questions? Okay. Let me also make another announcement. There will be no class. We will not have a formal meeting on Friday. I'm going to give you something to do, and since it, well, hopefully it'll be kind of fun to play with. And I will also assign class homework, which will involve a little bit of these applications. Won't be too taxing, but I'm going to give you an exercise with regard to Rubik's Cube. I've got to be out with the calculus challenge, and there's really no good way to have somebody substitute for it now. So anyway, I'll give you something to think about. So we were going to spend the last, I'm probably just going to spend one day talking about cryptography, just to kind of give you an overview. And then we're going to apply some. So this is applications of Chinese remainder theorem, finite fields, all that this we're talking about. How many of you heard of RSA cryptography? Or perhaps public key? Y'all run across this. Do y'all know how it works, or is it just something that you kind of heard? It's an incredibly clever way to hide things. The idea behind this is, and of course, we experience this every day. I mean, if you've ever done anything with a credit card online, or, you know, sent an email that you didn't want anybody else to see, or something of this nature, then this is probably what helps you out. So the problem at hand is this. Indeed, or two people. And of course, it's important to do lots of communication private. You want people having access to your bank account, all kinds of other stuff. Just ask Brett Favre. It's not good if you can't communicate privately. So this is the thing. Of course, you want to use the internet or something like this, where somebody else might intercept your transmission. So how can you and I communicate? And anybody that intercepts our transmission can't do it. Have you ever seen the movie The Imitation Game? Anybody ever seen that? Right. So that was the big World War II thing. The Germans had this big machine for encrypting things called Enigma. It was very old-fashioned by our standards today. And of course, the Allies were intercepting these communications every day, but they couldn't tell what it said. It was gibberish, right? So we want to do something like this. I want to communicate with you. I want you to be able to read it, but if you intercept it, I don't want you to be able to interpret it. So how do we do this? What's the step to do it? Well, the idea, if this is a terribly clever idea, we hope to keep time. Now, what do I mean by this? Well, the idea is two people that want to communicate, A and B. Public one. I'm going to show you how to sort of generate these things. So the public key public key, and it consists of two numbers. We will say NA and Y. So what do I mean by public key? I mean, I've got these two numbers. This one especially is very large, and usually Y is large as well. These are just two numbers in some range, right? Maybe NA is maybe 100 digits long. Now, what do I mean by public key? I mean, everybody can see this, right? Maybe I've got a website and I just, here's my public key, right? And I give the entire world this information. And I have a private key. Excellent. This one's secret, right? I know it, I've got it under my pillow or in my mattress or whatever, but I don't tell anybody this. Only I know private. I'm going to use a similar notation for B, but I'm going to use some public key. And B, YB, and private key. And what I'm going to do is, well, the first thing I'm going to do is I am going to sort of tell us the message. That is to say, suppose I am A and you're B. When you send me a number, or when you send me a message, your message to me is scrambled using the public key. So it's this unrecognizable mess. It's another number, and I can unscramble it and find the number that you gave me. And so the numbers can basically, I mean, you can do it as simple as this. Maybe you send me a bunch of messages, right? And you want to say, hi, Jim. So you take H to be whatever letter of the alphabet that is, right? The eighth letter or whatever, HI. So you go 8, one message 8, one message 9, and then you spell Jim, whatever. And you send those 5 messages to that. Now you're going to input these numbers. The public key is going to scramble it. So if you intercept what he sent to me, you see this huge number and you've got no idea that the original one is an A. But somehow I've got to be able to get that original thing out so I can read the message. So in practice, what happens is your messages are actually converted to some string of numbers or whatever. I'm oversimplifying it, but basically the principle here is the same. So my messages will be consisting of some number mod NA. So this will be a number between 0 and NA minus 1, right? And of course, this is 100 digits. A lot of messages you can send that way. Okay. And here is how the public key private key works. So the idea is So so here is and usually there's smart ways to do this to make it even harder to break, but I select a public, YA as part of my public key. Notice that in this little, in this equivalence equation here, notice my public key shows up, my YA and my MA. And XA is the private key. I don't tell anybody this. So I select my private key, given my public key that I picked, I figure out what XA has to be. And of course, the same as B. Now, in principle, N could be about anything, but the way it's done, the most efficient way it's done, uses select NA and NB to be provided to very large prime numbers. There are certain rules that you want to conform to in the selection of this. You don't want to select prime numbers 3 and 7 because that's so small, you're going to see it'll be easy to break that code. But you pick very large primes, and usually you pick these fairly close inside in the big picture thing, but like maybe an order of magnitude apart, right? Something like that. So they're fairly close, but they're both very large, not too very far apart. Here's the process. B wants to send a message. And B wants to encrypt it so that nobody else can see it. D converts message to number. So whatever this message is, Jim, you understand the class, whatever, you convert this to a number, right? That I will be understand. Now, what does B do to hide this message? 3, B uses a public key to convert this. So you take whatever number this message is that I'm going to understand, and the world could perhaps understand, and you scramble it. And how do you scramble it? Well, you look on my website and say, okay, Jim's got this private key or a public key YA. Take whatever that number is, take it to that large power, modulo NA, right? So maybe you take a big power and it's bigger than that, and you can divide out and take this equivalence class mod in that. So, for example, well, I'll actually. Now, this is very unlikely this is the same as the original message. And even if it were the original message, anybody intercepted would be suspicious because they would think it would actually be a scrambled message, right? It's very unlikely this is the original one. It's probably going to be some different number. Probably. So basically, to somebody that intercepts this, all they can read is they don't know what M is. They just got this other string of digits. Now, they know my public key was YA. So if they could somehow take the YA root of that, they could break this, right? But how do they do that, right? I mean, taking the YA root of that, that's very difficult modular arithmetic. But I can read the message. They see something that's gibberish, but I can. But let's notice that it's actually not one mod in, it's one mod feed. I think I may have put that. This is odd. Where this is the Euler feed function. Because here's what happens. There's the mess that you sent, right? Now I take your mess and I take your mess to this power, right? I just take power, and that's fairly easy to do. But YA XA is equal to 1 mod phi. And remember, when you do the Euler phi function here, we have M to this power. This is the same thing as 1 mod the Euler phi function. And so basically, by taking my secret private key, when I take your gibberish to that power, it fixes the exponent back to 1. And now, ding, 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 I've got your original message. But, okay. So let me give you a simple example that we can do by hand, and I'll kind of ramp it up a little bit. So for example, so by the way, using this part of your public key is a terrible idea. 50,000 is way too small, but I want to actually do something concrete that we can see. Okay. What's the Euler phi function of this? Well, the Euler phi function is phi 5 left And of course, these are both prime, so this is 4 times 10. So I want to pick something that's relatively prime to this. So yeah, let's just make it easy. So I pick public key. Uh, 55 and this is my in-survey, and this is my class. Now, this is my public key. I put this on my website and said, hey, I'm using 55, and this is how you scramble me, you just cube stuff, right? Now, what I want to do here is I need to figure out what my private key is. Now, what's my private key? My private key should be the inverse of this thing. So find 3 inverse mod 40. Notice it's important that I'm relatively prime to the Euler phi function, right? Because I need 3 to be relatively prime to 40, because otherwise it's a 0 divisor, and I'm never going to be able to invert it, right? So that's another kind of, there's the theory here. I need 3 and 40 to be relatively prime, no problem. Any ideas?
Why do you find the inverse of y?
Because that's how I'm going to unscramble it, right? So when you send me a message, the power of 3 scrambles it. So at this point, all I've got is gibberish. So I need the inverse of that to unscramble, right? I'm going to do a more sophisticated example of this, but if I want to find the inverse of 3 mod 40, I can use the Euclidean algorithm to follow the play. I'm going to run, so I'll do a couple of seconds. Euclidean algorithm. 40. By the way, the greatest common divisor of 43 is 1, so I should eventually get to 1. And I'll get there pretty quick. Okay, 40, if I divide by 3, I get 13, remainder of 1. Everybody agree? I'm already there. That's the greatest common divisor. Right? What does this mean? This means that 40 plus 3 times negative 13 is 1. Right? And this tells me if I reduce mod 40, that's 0, 3 times negative 13. So in this case, it's 27. because -13 is the same thing as 27 mod 40. I can also use -13.
But okay.
Okay, let's send a message. Okay, somebody give me a number, don't make it too small, between 1 and 55, don't send it. Actually, make it a big one, reduce by 55. Lucas is just dying to tell me, right? So he's got to communicate that to me. But he doesn't want anybody else to know for whatever reason. So Lucas takes his message and he says, okay, Jim's got public key of 40. So let's see what happens. Here's what happens. So Lucas gives me 85184. But we're going to reduce this mod 55. Oh, yeah. So Lucas's message is 44. That's a scramble, right? Why is that? What happened there? You know what it is about Lucas's message? Maybe be the same. Because we're going mod 55. The mod 40 is for the exponents. That's what's a little bit different. What was unusual about Lucas's message? I didn't pick this up when you first said it. I'm glad you said it. It has an 11 in it, right? Lucas's message is still bona fide. It's just not as interesting as an example, right? Because what will happen is you'll get that. So everybody sees the message 44. Now, all you scalawags out there may think, well, this maybe something else scrambled. But that's okay, because what I'll do is I'll take M to the 27, which is using that's my private key. Which is 44. So I get his message back, but it's not that interesting. Let's try another one. Send me a message that is divisible neither by 5 nor is it divisible by 11. New message. Give me something between 1 and 55 that's divisible neither by 5 nor 11.
16.
How about 16? What happens if you message it with 16? Well, he does a scrambling bit. And 16 cubed is like 4,096. Yeah. And mod 55. So this is scrambled into 26, right? So you all see, I mean, it's only a 2-digit number, but you all see gibberish. You don't see this original message. Now me, I take this message. Now I apply my private key. And so I'm going to take your message, 27 pound. And I suspect But the 27th power is a little bit too big for my calculator to handle in an efficient manner. So here's what I want to do. I'm going to take the modular steps along the way. What's 26 cubed? I get 17,576. It's already getting too big, so let me reduce this mod 55. Oh, that's better. This is actually 31. Let's do it again. 31 cubed. $31 cubed is 29,791. And that's 36. And finally, here's one true. This is 46,656. And mod 55. So I have successfully read with this method, right? Scrambled this, making it indecipherable. Well, not easily decipherable to you all here. But then when I attach my private key, which you all don't know what it is, and bang, 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 I get the message back. Let me do another example. Any questions? How do I do what?
How are you finding that?
Oh, how do I do that quickly? So here's what I did, actually. Here's what I did in my calculator. I took this and divided by it because I wanted to find out what this is, mod 55, and I didn't want to divide everything by the remainder. I divided this by 55, and I got an integer with some decimals out. I made like Henry VIII and cut the head off that thing. So I took off the integer part, and I've got just the decimal part left over, and I multiplied that by 55. And that is, that's an important way to do it. Yes.
What's stopping somebody from finding the private key for you if they have some?
That's a great question. So let's actually do one more example here. So I'm gonna do one more for finding a public and a private key here that has a little bit more of the Euclidean, and then I'll address that question. So okay, let's do a little primes that are a little bit more ambitious, like that. And you can trust me, these are both primes. My public key, the N, is 503 times 1867, which is something like 939101. Right, okay, this is a little bit bigger. Although, again, for a computer, this is trivial to find. Maybe it's trivial, but like any good mathematical software, it will immediately give you an answer. Okay, we need the Euler phi function for this. By the way, N is public. This is N goes on the website. The Euler phi function is not, right? Because if I walked up to you on the street and told you that I said, I don't know how to factor that. You have to test its prime. You don't know what the factors are. You got to figure that out. If I tell you what this is, you can probably figure out how to factor. This is not public. This turns out to be 936732. So my public key in this example is 939.101 and 11. I just picked 11 because the exercise here, what we want to do is try to explain how it is that I get my private key out of that. Okay. But how do I find my private key? So what I need is and notice, by the way, again, 11 is relatively prime, this thing. In fact, I think this is 2 times 251. So the primes are divided as 2, 251, and 3, this is 2, 251. This is 2 times 3 times 311. And 251 and 311 are both prime. They don't involve 11, so I'm good. I need 5 11 inverse mod 9, 3, 6, 7. And you can do this by the Chinese remainder theorem or whatever you want, but I'm gonna use Euclidean algebra. I will execute it over here. So the greatest common divisor of 11 and 9,36732 is 1, right? And I'm going to show you how you can get 1 as a linear combination. You all remember that? That was a big thing we had early on, that the greatest common divisor is a linear combination of 2. I'm going to show you how to do it. The Euclidean algorithm shows you how to do it. So let's take 9,36732 and divide 11. So what I got was 9,36732 was equal to some big number here, 85157. 11, and it had remainder 5. Now, take what I divided by, the 11, and write 11. Now, divide 11 by 5. So I get 11 is equal to 2 times 5 plus 1. And there. So you keep doing these remainders until you get the greatest common divisor. And I've worked my way down to 1 and there we go. Now, how does this show how to write 1 as a linear combination? Well, you just patch it back together. And here's what I mean. Right? 1 is 11 minus 2 times 5, right? Now go back up here and I can rewrite this 5 as whatever this 5 is. It's 936,732 minus 85,000. 7 times. And this will give you 1 as a linear combination. So let me kind of rewrite this here. So one is here. Let's see, what do we get here? That's going to be 2 times this, which is, well, so 1 is 11 minus 2 times this business, which turns out to be 170, 315 times 11. When you straighten this all out, so it's minus 2 times this, and then plus another 1 times 11. Minus 2, 9, 3, 6, 7. So reduce this mod 93672 to a thing that 1 is equivalent to so this is my private key. It's the inverse of that. Let's listen to my modules. 170.
Yeah, 11 minus 2, everything comes 6 to the next one.
Yes, I did. So
What happens to the first one?
it's absorbed into this. So 2 times this is 170,314, and then there's one more. Right, and so I think Coleman's point is taken, right? If this was fairly easy, wasn't it? I mean, I don't even think I used my calculator on that one, right? And I got the inverse of 11 mod 936,732, right? So once I gave you what your public key was and what, well, the modulus and your scrambler, right? The exponent thing that I want you to use. Then finding the inverse 11, not too shabby, right? But if I just give you these 2 numbers, finding this, because there's one thing that kind of we sort of skipped over a little bit. I didn't just give you this. I gave you the 2 primes factored into 503 and 1867. What this public key cryptography is predicated on is it is very hard to factor these numbers. So let me kind of go a little bit deeper into that. So let me pick another 2 primes, and this is by hand. Yeah. Most useful number in the world. Okay, these 2 numbers are prime, right? Prove it. I mean, how would you do it? Even the small one, 8675309, that's 8 million. That's right. That's over 8.5 million, right? How are you going to check whether or not that's prime? Well, let's see, shall we? It's not even. Y'all know the trick for testing if it's divisible by 3. If you add up the digits and it's divisible by 3, well, you can add up the digits not divisible by 3. Well, it's pretty obviously not divisible by 5. Now 11, there's a trick for 11 too. The 13, 17, 19, it gets out of hand, right? And here's another thing. You have to have an exhaustive list of primes. How do you know what to check? We certainly don't want to waste your time checking every odd number, like 25 is a waste of time. I multiplied this out and put it into Maple, which is a pretty good mathematical software thing, and it immediately factored, right? I doubled digits on this, and it took a while, right? This problem is harder and harder as the lengths of the primes grow. So let me kind of give you some perspective. If I give you this number, it's about a 15-digit number, right? If I multiplied it off, it's like a 15-digit number. And I said, okay, just use your calculator and tell me if this number is a prime or not. How long would it take, right, for this 15-digit number? If I said, find the smallest prime, and you went through and you checked all the primes in order, 2, 3, 5, 6, and 5. There's a couple of things here. Number one, I'm assuming that you have a table of primes, which the question becomes, how did you get the table of primes in the first place? Because it's hard to determine what something is. And second of all, let's assume that you could check one prime. So you have this number and you check for prime divisors. Suppose you check one prime a second, right? Well, 8675309 is the 582,161st prime, right? So you would have to go through that many primes if you're testing in order to get this. So if you could do it on your calculator and test one prime per second, it would take you 6 days, 17 hours, 42 minutes, and 41 seconds to find the smallest prime divisor. Now, okay, that's kind of stupid, right? Because we're humans, and that's why we invented computers, is to go faster. And computers do go faster. However, they've got limits as well. So here's kind of some stats on what computers can do now. So they actually do research on this. How fast can you break these things? It's a big computer science thing. If I give you a 2' composite, how quickly can you break it? Well, a 232-digit prime number, or a 232 prime composite like this, right? 2 primes, 232 digits, was broken 2 years ago, and it used multiple computers, right? If it had used a single computer, it would have taken, instead of 2 years, it would have taken about 2,000 years, so about 2,004 years to factor a 232-digit prime. In the RSA competition thing, they have no prime, they have no composites over 250. They've been broken. You might go try them just for fun. Some of them have large cash prizes attached to it, as a matter of fact. But 250 digits, and I think they've got one, it's like 600 digits, and they're like, this just really can't be done in practical time with what we have now. Now, of course, the computers are advancing fairly rapidly. And in fact, when I was, so in the mid-90s, they did a contest similar to this, and they multiplied a couple 64-digit prime numbers. And of course, you get something like 128, 129 digits like that. And it took, I think, 5 years for a bunch of people working together to break this down into the 2 prime composites. And at the time, if they had used techniques that were 5 years older, it would have taken longer than the age of the universe to find those two. Now, that's where we're at right now in RSA, and it's still a secure system because, and this is a basic thing, right? Everybody knows 6 is 2 times 3, but when you got bigger digits, it's very hard to do, and there's no polynomial time algorithm, no factor primes. Now, if they ever get quantum computers up and running, you should probably take your money out of the bank and put it in your mattress until they figure out better algorithms. But actually, their RSA isn't the only thing. There's elliptic curve algorithms, and there's lots of number theory and math that go into doing this kind of stuff. Okay, any questions? Any questions? So do you guys kind of get the gist of this? And hopefully you see a lot of connections and stuff we have about the GCDs, the Chinese remainder theorem, and, the oil and fee function and Lagrange's theorem and stuff. Okay, there will be no class Friday, so here is my duty for you all. I know it's really, really tough. I'm gonna need these back at the end of the semester. I'm sorry about that, but. What's this? 2, 3, 4. Can you solve it? Bite the bullet and scramble the thing. Don't worry, I can get it back. Did you get it? That's right. And you know what the problem is? If I do this, and then do them in the other order, if everything commuted, that would be back to the starting position, but it's not, right? So that's, so scramble this thing. What I want you to try to do, in your time, did I give you one for?
Oh, there's sweet cubes.
Was it?
Nice.
How many of you, do any of you know how to do it already? So did you figure out how to do it, like some algorithm off the internet or something like that?
Every scheme has like they have like a method for it, and they teach you like all this stuff.
I'm gonna show you how to do it by just the first principles. Like, you can, the first time I ever did it was we put some piece of paper, and I'm gonna show you how you can do this.
Really?
So my project for you, I've got one thing to do. See if, play around with these things and make yourself confident enough to where you can get one side, right? So, and one side correctly, like, for example, when I say one side, solve it. Let me do something like that. So one side correctly, just like this right here, just one layer, and then I want the color correct. Right? See if you can do that, and that'll make it more fun. Okay, other questions? If you're out there in Etherland, I can't get it to you, so you'll have to come to my office. Pick it up. Any questions? All right, I will catch you guys on the flip side then.